Hello friends, now we are going to talk about the last topic of this chapter, that is Clausius Clapeyron's latent heat equation. Now let's talk about the first equation. There are two equations, so we'll talk about the first equation right now. Now until now we have seen the many processes which are changing their phase from the one to the another at something like when the volume is getting changed, or else the temperature is getting changed. Now what is happening when the process is changing, or the changing its states, or the phase is getting changed, right? So at some changes happening and the pressure, right? So the when the processes or the substance is changing its state at or at we can say the when with pressure is changing, or the variation in its pressure, when the substance is going from the one phase, that is solid state, to the liquid state, or liquid state to the gaseous state, right? So the this latent heat is nothing but the heat radiated or the absorbed during the phase transformation. Okay, so when the phase is just getting transformed from the one to the other one, then how much amount of the heat is getting absorbed or the radiated is nothing but the latent heat, right? So now this equation, or this latent heat equation, very useful to explain the variation of the melting point of the solid with the pressure, or else the variation of the boiling points of the liquids with the pressure, right? So this is what we are going to talk about within this equation. So now is very these equations are very applicable to the substances which are uh, undergoing with the change of the uh, phase of the first order only. So is also known as the Clapeyron's equation. Let's try to look into the this figure, that what it shows is nothing but the indicator diagram at the some isothermals, right? So it is also known as the isothermals in the say that the PV diagram plotted at the some constant temperature, so the is called as isothermals as well. So the isothermals which is plotted here is the A, B, C, D and G, H, I, J are the two isothermals at the two different temperatures. So the temperature corresponding to this is at the temperature is T, and for the another process that is going for GHIJ, that for that curve it is T plus dt, some small change in the temperature is there, right? So these are at the very below the critical temperature isothermals are, okay. So now it both the processes are going through the three different processes, okay, or three different parts, right? So it consists of the three parts, that is AB, BC and CD, just such as also the GH, HI and IJ. Okay, similarly we can just talk about when the heat is absorbed by the substance in a liquid phase, it expands isothermally along the AB, okay, and at the point B, okay, at this point B, it starts converted uh, into the vapor, okay. So now this is expansion, and then at the point B it starts converted into the vapor, and its pressure is P, okay, its pressure is P and temperature is T, remain constant during this curve BC, okay. So you can see the straight line curve parallel to the volume axis, right? Both remains the constant, okay. At the point C, okay, it is purely the gaseous phase, okay. So this is the purely gaseous phase, and thereafter obviously if it is gaseous, then obviously it obeys the Boyle's law, okay. So during this curve CD, okay, so it obeys the Boyle's law, okay. Then similarly we can explain the another curve, that GHIJ, okay, it can be explained. So along the HI, the change HI, the change of the phase takes place at the constant pressure P plus dP, and temperature is T plus dt, okay. So do remember it. So they are at the difference. Let's try to join the two curves, 2 points, that is H and M, and I and n by a dotted line. So the closed curve or closed figure HINM can be regarded as the one of the Carnot cycle. So it looks like a Carnot cycle, right? So this is something if I just plot like this and like this, so it is something like, okay, it looks like a Carnot cycle, right? So let's suppose that the unit mass of the substance is taken along the HINM. Okay, HINM unit mass is just taken. Now along the HI, so unit mass of the substance absorbs the amount of the heat which is equal to the L plus DL. So the amount of the heat absorbed along HI is how much? Is the L plus DL at the temperature T plus dt. So its volume increases from the volume increases from the V1 to V2 isothermally, isothermally and uh, isobarically, isothermally and isobarical, that is at the constant pressure and the constant temperature. So the liquid is converted into the vapor. So in this case liquid is converted into the vapor. So the increase in the latent entropy, so the increase in the entropy at this point, or increase in entropy is given as L plus dl upon T plus dt. Okay, so again along the IN, so along the curve IN, what happens that the substance expands adiabatically. So this is an adiabatic process and its temperature is decreased from the T plus dt to T, and the pressure is decreased from the P plus dP to P. So there is no change in the entropy, because during the adiabatic process there is no exchange of the heat, so there is no increase or decrease in the entropy. So entropy remains same along the along IN, no change in entropy. Getting it? Okay, so now the remaining curve, that is along the NM, along the NM, the substance gives out the heat equal to the latent heat L at temperature T, because we are at the temperature T. So it gives out or radiates its heat energy, and the that is equal to the latent heat at that particular temperature. So the vapor is converted again back into the liquid, because volume has decreased. So there is decrease in the volume from the V2 to V1. So the decrease in the volume from the V2 to V1. Okay, so isothermally and again the isobarically. So the decrease in the entropy. Okay, so now here decrease in entropy is L upon T. Okay, so this is given. So the along the curve MH again, when we come back, along this curve MH, again the temperature is increases from the T to the T plus dt, and pressure is increased from the P plus P to P plus dP. So the original state is, or we have reached our initial state. Okay, so initial state has been restored. So this is the one of the cyclic process, right? So we have just completed the cyclic process. So during this cyclic change, the net amount of the heat absorbed by the unit mass of the substance, during the cyclic process, amount of heat absorbed is given by dq is equal to L plus dl, plus there is no work done, because we have reached no internal change in internal energy, or no work done. So L plus dl plus dq minus L, this is something like a dq. So the dq is change in the its change in its heat absorbed or the evolved is equal to the change in its latent heat. So dq is equal to dl. As the original state has been restored, so the no change in its internal energy, so du is equal to 0. So now during this process, how much is the work done? Work done by the substance is equal to the area under the closed curve HINM. So area under this curve. Now, if suppose there is some change in its temperature, a very small change, that is dt is infinitesimal change in temperature, then the HINM is regarded as a parallelogram. So HINM is regarded as a parallelogram. So the how much is the area? Area is nothing but the work done. So base into the height. So this is area of the parallelogram. How much it is? So v2 minus v1 is its base, and how much is the height? Height is nothing but the difference between these two, p plus dp minus p. So this is given. So work done is nothing but the dp into v2 minus v1. According to the first law, dq is equal to du plus dw. So dq we know that is dl, and du is 0. So dw is nothing but the dp into v2 minus v1. So again, trying to consider the second law of the thermodynamics, that is change in the its entropy is given. So change in entropy in the reversible cycle is always 0. So what we can, L plus dl upon T plus dt. This is what we have seen in this first case, that is heat absorbed along this is L plus dl, and the entropy change has been given here, increase in the entropy and the decrease in the entropy. So difference between remains the 0. So this gives us the equation L plus dl upon T plus dt minus L upon T. So this gives us the dl is equal to L into dt by T. So just try to substitute this back into the earlier equation here. So L dt by T into dp into v2 minus v1. So you just try to rearrange the term. So dp by dt, so change in the pressure with respect to the temperature is given by L upon T into v2 minus v1. So this is known as the first latent heat equation. Okay, so or else now here it is also known as the Clapeyron's first latent heat equation. So the here work is expressed in the joules, and heat is expressed in the calories, right? So therefore this equation can also be written with the some mechanical equivalent of the heat, that is J. Okay, so 4.18 right. So that is mechanical equivalence corresponding to it. So calories, right? So we can have the dp by dt is equal to L J upon T into v2 minus v1. Okay, now what are the applications of this equation? That is one of the application is the effect of the change of the pressure on the boiling point of the liquid. So when we are just trying to convert the liquid into the vapors or in the gaseous state, so the amount of the volume is always greater than the amount of the volume amount of the volume in the gaseous stage is always greater than the amount of volume in the liquid stage. So the what we can say, the v1 or v2 is always greater than v1. So this is something like in the liquid state, and this is in the gaseous, this is in the v2 in the v in the gases is always greater than the v in the liquid state. So what we can say, the dp by dt, okay, dp by dt is always greater than 0, or it is a positive. So what we can here consider that with the increase in the pressure, the boiling point also increases, and vice versa. The liquid boils at the lower temperature when the pressure is reduced, and when the pressure is increased, the boiling point also increases. So this principle is generally used in our home appliances as like a pressure cooker, right? So what is inside it? That is, water boils at the higher temperature because of the pressure inside it is more, right? So that's why the cooker is for the that's why we use the cooker to pressure cooker to boil the vegetables in the quick action, right? So in a smaller amount of the time. The another application of the this equation is the effect of the temperature on the melting points of the solids, right? So when the solid is converted into the liquid, and obviously there is a change in volume, right? But in this case there are two cases, right? There is a possibility that the volume of the liquid is greater than the volume of the solid or vice versa, right? So for a substance which expands on melting, okay, so the volume of the liquid is greater than the volume of the solid. So in such a cases, what we can have is the dp by dt. Okay, dp by dt is a positive quantity, so we can get the similar kind of the result, right? So it means that the change in the pressure with respect to the temperature positive gives the melting point increases with the increase in the pressure. And on the other hand, for the substance which contracts on the melting, the volume of the liquid is less than the volume of the solid. In such a cases, dp by dt is always less than 0. Okay, so or this is becomes a negative quantity. So the melting point decreases with increase in the pressure, such as the ice contracts on melting. So this is uh, the first equation of the Clausius Kaplan's latent heat